Why building a brain-sized chip is next to impossible. In the quest for ever greater computing power, the idea of building a computer chip as large as the human brain is a tempting fantasy. The brain, after all, is nature's unmatched processor, packing the power of around 86 billion neurons and trillions of connections into a 3-pound mass. But in the world of electronics, the notion of creating a monolithic, brain-sized chip quickly runs into a wall of harsh, inescapable realities. These limits aren't simply a matter of cost or technological skill. They are written into the laws of physics and the practicalities of materials science. Propagation delay, the speed of light as a hard ceiling. The most fundamental barrier to a brain-sized chip is propagation delay, the time it takes for an electrical signal to travel across a material. In modern CPUs, the clock, the signal that synchronizes every operation, must reach every part of the chip almost simultaneously. This requirement puts a tight leash on chip size, because signals in silicon move at about half the speed of light in a vacuum, roughly 150 million meters per second. At today's clock speeds, typically several gigahertz signals have only a tiny fraction of a nanosecond to traverse the entire chip. For example, at 3 gigahertz, a clock cycle is just 0.33 nanoseconds long, which means a signal can only travel about 5 centimeters in silicon before the next cycle begins. The human brain, by comparison, is about 15 centimeters wide, far too large for a synchronous signal to cross in a single clock cycle. This makes it physically impossible to operate a brain-sized chip as a single, high-speed processor. The result would be chaos. Different parts of the chip would be hopelessly out of sync, leading to logic errors and system failure. Manufacturing, yield defects, and the limits of silicon wafers. Modern chips are manufactured on circular silicon wafers, typically 30 centimeters in diameter. Even with advanced technology, it is difficult to make a single flawless chip much larger than 2 to 3 centimeters across. The bigger the chip, the more likely it is to have microscopic defects that ruin its function. Making a chip the size of the human brain would be like buying a lottery ticket for every square millimeter, and almost every ticket would lose. The yield usable chips per wafer would drop to nearly zero, making the approach financially and practically impossible. Heat and power, a thermal nightmare. Chips generate heat, and the bigger the chip, the more heat it produces. A brain-sized chip packed with billions of transistors running at THz speeds would dump out far more heat than any cooling system could possibly handle. Overheating would lead to rapid failure, thermal expansion causing mechanical stress and cracks, and ultimately meltdown. Today's CPUs already struggle to dissipate heat at much smaller sizes. Scaling up by a factor of hundreds would quickly become catastrophic. Electrical wiring, capacitance, resistance, and signal degradation. As chips grow in size, the wires connecting different regions become longer. Longer wires have higher resistance and capacitance, which slow down signals and cause them to lose strength or become distorted. The more you stretch a chip, the worse these effects get. At the scale of a human brain, the wiring alone would act as a huge brake on any attempts at high-speed computation, fabrication and assembly, physical and economic limits. Even if it were possible to make such a massive chip without defects, handling, packaging, and assembling it would be a logistical nightmare. Silicon is brittle. Large pieces would be prone to cracking or breaking during fabrication, transport, or operation. The sheer cost of producing, testing, and deploying something so large would be astronomical. How the brain gets away with it. It's worth noting that the human brain is able to operate at its size because it is fundamentally different from a digital computer. The brain is massively parallel and asynchronous. Each neuron operates independently and at very slow speeds measured in hertz, not gigahertz. There is no central clock, no need for every cell to be in perfect sync, and the entire system tolerates slow, lossy, and unreliable connections. Electronics, by contrast, rely on extreme precision and timing, qualities that become impossible to maintain at the scale of a human brain. The only way forward, modularity, not monoliths. Modern supercomputers and data centers achieve high performance not by building giant chips, but by connecting many smaller chips together. Each chip operates in its own clock domain, and they communicate through high-speed networks. This modular approach avoids all the worst problems of propagation delay, manufacturing yield, and heat, at the expense of complexity and some communication overhead. Conclusion: the dream of a single, brain-sized chip is blocked by hard, immovable limits. The speed of light, the realities of manufacturing, the brutal facts of heat and power, and the unavoidable problems of wiring and defects. In the end, the only practical path to brain-scale computing is not to scale up a single chip, but to scale out building networks of many smaller, coordinated systems. Nature's solution, as always, is parallelism, modularity, and compromise, not brute force or endless scaling. The core issue, propagation delay, in the design of modern CPUs and high-speed digital circuits. Propagation delay is one of the most fundamental and limiting physical constraints. As engineers strive to make processors faster and more powerful, they encounter a wall that is not just economic or technological, but rooted in the basic laws of physics, the finite speed at which electrical signals travel through materials. What is propagation delay? Propagation delay refers to the time it takes for an electrical signal to travel from one point in a circuit to another. This delay is not instantaneous even though signals travel fast. Their speed is limited by the properties of the material they move through. In the case of CPU chips, signals move through silicon and metal interconnects, where the effective speed of signal propagation is much slower than the speed of light in a vacuum. In silicon, signals typically propagate at about 150,000 kilometers per second, roughly half the speed of light in a vacuum. But this is still a hard ceiling that can't be exceeded. When designing logic that operates at gigahertz speeds, billions of cycles per second, even picoseconds and nanoseconds of delay add up quickly. Why propagation delay matters in CPUs? A CPU operates on a global clock signal, which coordinates when each part of the processor performs its next action. For this system to work, the clock must arrive at every point on the chip nearly simultaneously. If the distance between the farthest points on the chip is too great, or the clock signal travels too slowly, parts of the CPU will be out of sync. This is called clock skew, and it can cause computation errors or outright system failure. At high clock speeds, the amount of time available for a signal to propagate across the chip shrinks dramatically. For example, at a clock speed of 3 GHz, a period of 0.333 nanoseconds, a signal in silicon can only travel about 5 centimeters before the next clock cycle begins. If the chip is larger than this, it becomes physically impossible for the clock or any signal to remain synchronized across the entire chip. Consequences of propagation delay. Propagation delay fundamentally limits how large a synchronous single-clock CPU can be. As the clock speed increases, the maximum possible chip size decreases. In the early days of computing, chips were slow enough and small enough that propagation delay was not a practical concern. But as manufacturing processes improved and chip designs became larger and faster, propagation delay emerged as a critical bottleneck. Today, most high-performance CPUs are constrained to die sizes around 1 to 2 centimeters per side. Making chips larger would require either lowering the clock speed or risking synchronization problems, both of which are unacceptable for modern computing needs. Engineering workarounds. To cope with propagation delay, engineers have adopted a number of strategies. Multiple clock domains. Instead of synchronizing the entire chip to a single clock, large chips are often divided into smaller regions, clock domains, each with its own local clock. Communication between domains is handled asynchronously or with special synchronization circuits. Pipelining. CPU designs use pipeline stages to break up long signal paths, allowing each stage to complete in a single clock cycle. This helps, but does not eliminate, the limitations imposed by propagation delay. Buffering and repeaters. On long signal lines, additional circuitry buffers or repeaters is used to boost signal strength and minimize distortion over distance, though these add their own delays and power costs. The inescapable limit. Ultimately, Propagation delay is a law of nature. No matter how advanced fabrication techniques become, signals can only travel so fast through matter. This fact sets a hard limit on how fast and how large a synchronous chip can be. As clock speeds rise, the only way to build larger systems is to abandon strict synchrony, leading to more complex, less elegant architectures and more engineering challenges. Conclusion: propagation delay is not a minor technical detail. It is a core barrier that shapes the entire landscape of computer architecture. It is why CPUs are the size they are, why clock speeds have plateaued, and why engineers spend so much effort on workarounds like multiple clock domains. The speed of signals in silicon is a brute fact of physics that cannot be ignored or bypassed. Any attempt to scale up or speed up modern digital logic ultimately runs into this wall, making propagation delay a central and unsolvable problem in the quest for faster, more powerful computing.